this video, we're going to solve two types of equation, exponential and logarithmic. So we'll have different methods for each, but they're both closely related. So it'll be important to realize first which type of equation we're working with. Okay, so first I want to start with an example we've already done, but we're going to look at it in a slightly different way. Okay, so this is your compound interest formula. You've seen this before. You got $5,000. You're going to invest it. So I could write the function. It's a function of time. It's my initial amount times 1 plus my interest rate, which is 4.5%, 0.045, over 10 years to the rate times time. Okay. So let's see. You want to invest 10,000. So I can figure this out. We've already done this before. Run this through my calculator. It tells me how much money I have. In 10 years at 4.5%, I probably won't double my money. My guess is going to be somewhere around $8,000 or $9,000. If I want to do this continuously, I'd set this up, and I have a different formula, right? Compound continuous is e to the RT, so 0.045 times t. In this case, t is 10. And I could have done that with the last one. I could have first built the function t. All right, so this is a function that with any time t, it'll tell me how much money I have if it's compounded monthly. Sorry, I have a mistake in there. N should be, try this again, to the nt. Okay, so that is, my formula is for compound interest, it's my initial amount, 1 plus the rate over n, not t, to the nt. That's what I should have had here. And this is a function that'll tell me how much money I have after t years. So I can plug in 10 and get my answer there. Same thing here. First I wrote the function, and if I want to know how much I have in 10 years, I put 10. And these should be pretty close. You can do this calculation if you want. My guess is, I don't know, $8,000 or $9,000. Now, that's easy. Just plug everything into your calculator. Now, here's the question: when will you triple your money? Let's focus on continuously for this one. So I had $5,000 to start, so I will have tripled my money at $15,000. So first, let's set it up. E to the 0.045 t, and the question is when. So we're ignoring the 10 now, because we want to know how long it takes to triple your money. Okay, and I'm forgetting the 5,000 initial amount. So it's 5,000 times e to the 0.045 t. Okay, now if I was solving this, the algebra, I would say, oh, this looks complex, so let's divide by 5,000. That's something we know how to do. And then we get the number 3, which kind of makes sense. 3 equals e to the 0.045 t. Okay, now here's the new part. This is an exponential equation. The variable is up in the exponent, right? So I'm going to have to learn a new technique to solve. And if I made you think about it, you might say, and I said, well, how do you get this t out of the exponent? This is what we don't like. We need this down. What property did we learn about with logarithms that allows me to do that? Well, it's this property. It's the log base a of a to the n. Remember this guy? If the bases line up, then the log cancels out with the exponential piece, and you're just left with the exponent. So in this case, we can use that because I have a base of a logarithm that I like, that I can use. If we don't do that, if this was like a 5, then log base 5 isn't necessarily something we like so much. So I can use this other property that you should remember. What's that? If the log is base a and the exponent's not base a, it still simplifies our expression. It brings that exponent down and leaves me with this constant term. I know that looks ugly, but log base a of b is just some number. Okay? So, in other words, if you can line the bases up, then do it. If not, then we'll force to use the other one. And we'll look at both of these in this video. Okay, so that means I can use log base e. That looks messy, but what does that right-hand side simplify to? It gets real simple. But if I take the log of the right side, I got to take the log of the left side. In this case, I'm using the natural log. All right. So think about it. What is the right-hand side equal to? Well, that's easy. The natural log of e to some exponent is just the exponent. So that becomes 0.045t. And then on the right-hand side, I got this guy. That's a little ugly. That's new for us. It's the natural log of 3. But this is a linear equation. Okay, so this is our first exponential equation that we're solving. So let's take a minute to think about this. This, don't be confused by the natural log of 3. That's just some number. I'm going to plug that into my calculator if I want to. I'll ask you for 2 answers. I'll ask you for an exact answer, which I won't need a calculator for. And then I'll ask you for a decimal answer. Okay, so this is actually now a linear equation, right? I have some number times t. That's linear. The slope of this equation is 0.045. It just happens to be equal to the natural log of some number, but that is just a constant. So what are my steps in algebra? Divide by 0.045. That gives me t by itself. And this is what I mean by exact answer. Now in this example, we probably wouldn't ever want to leave our answer like this because it's an application. So I would never say, the question was how long to double your money, or triple your money rather. So I would never say, oh, it would take me the natural log of 3 over 0.045 years. I don't think I'm going to say that. I would just take my calculator out. Which I'm trying to find. And I get 24.4 years. 24.4 years. Okay, and that's approximately. So we can use our approximate equal sign. So I'll ask you for your answers in 2 ways. And when we do these problems, a lot of times I'll give you both answers. This is what I would call the exact solution, although it's a little funny with the decimal in there. And this is the approximate solution. Okay, the key step, the new step for us is right here when we took the natural log of both sides. Okay, that's how we solve exponential equations. All right, let's do another one. Here's we can read this process on your own. The idea is to isolate your exponential piece, which I did here. I divided by the 5,000 first and got the exponential piece isolated, and then I took logs. All right. So there's 2 types. There's the one we just did where we take the log of both sides, but there's actually an easier type I want to bring to your attention. And this one we won't spend a whole lot of time, but you can solve these without logarithms sometimes. Think about this simple case. If 2 to the x is 2 to the 5, what's x equal? X equals 5. Pretty easy, right? That is, if you can write them with the same basis, then what you can do is drop the bases and equate the exponents. So my first example, I can do that. The thing is with these ones, you have to recognize that I can write 9 with base 3, right? Here's the trick to this one. 9 is 3 squared. 9 to the x is 3 squared to the x. And then my exponential properties say a base raised to a power. All that raised to the power is the same as raising it to the product of that power. And then once I have these equated, there's the same base, I can drop the base, and I say 2x equals 4, x equals 2. All right, and I can always check my work. If I plug a 2 in here, 9 squared, that's 81, which is the same as 3 to the 4th. Okay? Most of the time, so that's all I'm going to do with that one. Just think about, if I had, I just use base 3. If I had like 32 to the 2x equals 2 to the 4th. This is an exponential equation, right? The variable's in my exponent. But if I can somehow be able to do this as base 2, then it's a lot easier. And the trick would be recognize that as 2 to the 5th, right? That's 2 to the 5th. And then it's easy from there. 10x equals 4. 10 times x equals 4. No longer an exponential equation. And x would be 4/10 or 2/5, right? And you could always check your work here by plugging in 2/5 there. Okay, so look out for those. You need to know your powers of 2, 3, and 4. I probably wouldn't give you anything much higher than that. But it's a way to do, it's like a little trick for exponential equations that makes it a little bit easier. In the following examples, we'll use logs. And most of the time, we're going to be using logarithms like we did in this first example in order to solve.